This is an Edexcel Chemistry Paper, so GCSE paper, higher tier from June 21. When heated, zinc carbonate decomposes to form zinc oxide and carbon dioxide gas. A student investigated the decomposition of a sample of zinc carbonate. The student used the following method. The mass of an empty crucible was determined. A sample of zinc carbonate was placed into the crucible. The mass of the crucible and the zinc carbonate was determined. The crucible and zinc carbonate was heated for 5 minutes. The mass of the crucible and contents was determined. Figure 1 shows the apparatus used. Suggests how the student could confirm that the decomposition was complete. Your clue here is measuring all these masses before and after. When you keep heating it and measuring its mass, you want to keep repeating that until the mass no longer changes. So actually the easiest way of saying that is heat to a constant mass. Believe it or not, that gets you the 3 marks. It's a very succinct way of saying what I just said. The theoretical maximum yield of zinc oxide was 1.86 grams. The actual yield was 1.63. Calculate the percentage yield. So you use this equation. Percentage yield equals actual yield divided by theoretical yield times by 100. Make sure you're substituting everything in the right place. 1.63 divided by 1.86. Multiply that by 100 to get 87.6%. Another student carried out the experiment using a similar method. The student used a blue roaring Bunsen burner flame and placed a lid on the crucible. State why the student used a blue roaring flame and a lid. So there's 2 flames on the Bunsen, the roaring blue and the orange luminous one. We used the blue roaring one because it's the hottest. It's quite important if you're heating something like this. And why did we use a lid? In order to stop the zinc oxide escaping. The scientist John Dalton lived over 200 years ago. John Dalton suggested an early model of atoms. When Dalton first described atoms, he said that all elements are made of atoms. Atoms are not formed of any particles. All atoms of the same element are identical. Give 2 differences between Dalton's model of atoms and today's model of atoms. Okay, the smaller particle stuff we know is incorrect. The modern day atom has subatomic particles. It's got electrons, protons and neutrons. And remember, those neutrons and protons are found in the nucleus in the modern atom. Dalton also investigated different gases. One of the gases that Dalton investigated was ethene. The structure of one molecule of ethene is shown. Give the molecular formula and empirical formula of ethene. So the molecular formula is the actual number of atoms of each element, whereas the empirical formula is the simplest ratio. So if we start with the molecular formula, the actual number, how many carbons do we have? 2. How many hydrogens? 4. For the empirical formula, we want to make the simplest ratio of that, so that becomes CH2. Another gas that Dalton investigated was chlorine. Chlorine gas reacts with water. The 2 products are a solution of hydrogen chloride and the substance HClO. Complete the balanced equation for this reaction, including the state symbols. Lots of clues here. First of all, let's start with chlorine. It's a diatomic molecule, so it's Cl2. We've been told it's a gas. We're reacting it with water, which is a liquid, to form hydrogen chloride solution. The solution indicates that it is aqueous. So now we need to check to see if it's balanced. 2 chlorines on the left-hand side, 1, 2 on the right, 2 hydrogens left side, 1, 2 on the right, 1 oxygen on the left-hand side, 1 on the right. It's all good. Hydrogen chloride solution is acidic. The formula for ions is shown in figure 3. Give the formula of the ion in figure 3 that causes hydrogen chloride solution to be acidic. It's the H+ ion, which is responsible for making anything acidic, because hydrogen chloride solution is actually hydrochloric acid. An acid reacts with an alkali. Give the name of this type of reaction. That is neutralization. A sample of potable water contains impurities. So remember, potable water is water which is safe to drink. Why is this sample of water potable even though it contains impurities? It's because the impurities are harmless. It's still safe to drink. Wastewater can be used to produce drinking water. The process used includes sedimentation, filtration, and chlorination. What is sedimentation? In sedimentation, it's when the solids settle at the bottom of a particular container or inside a riverbed. But the point is they sit on the bottom. So that's why C here is the correct answer. State why the wastewater is filtered to remove insoluble solids. State the reason for chlorination: to kill bacteria. Some salts can be added to wastewater to remove impurities. In an experiment, different masses of salt A were added to 1,000 centimetre cube samples of wastewater. The experiment was repeated with salt B. The percentages of impurities removed from the wastewater are shown in figure 4. It was concluded that the best way to purify 1,000 centimetres cubed of the wastewater was to add 100 milligrams of salt B. Use the information about salt A and salt B in figure 4 to evaluate the conclusion. Well, if you actually look at the percentage of impurities removed, the best is salt A, 150 milligrams, so I don't think I necessarily agree with that. And so therefore we would point out that it removes, we'll quote that number there, compared with the 100 milligrams of salt B, which only removes 40. Yeah, because that salt A removed 48% of impurities compared with 40% here for salt B. Wastewater may contain phosphate ions, PO4 3-. Aluminium ions react with phosphate ions to form aluminium phosphate. Complete the ionic equation for the formation of aluminium phosphate in this reaction. Aluminium is in group 3, so it has a 3+ charge. We're forming aluminium phosphate. Look, this is nice. These ions balance out. So that's what we're looking for as our answer. Aluminium alloys are used instead of pure aluminium in aircraft manufacture. Explain in terms of the arrangement of metal particles why aluminium alloys are stronger than pure aluminium. Because the atoms in the alloy are different sizes. This distorts the layers, meaning that the layers can't slide over each other as easily, so it's stronger. A 695-gram sample of an aluminium-magnesium alloy contains 2% by mass of magnesium. Calculate the mass of aluminium in this sample. Be very careful. It gives you a number relating to magnesium but asks you about aluminium. It's 98% aluminium. So we're going to do 98% of 695 to get a value of 681.1 gram. Figure 5 shows a graph of the relative strength of aluminium-magnesium alloys when the percentage by mass of magnesium in the alloy is changed. Describe what figure 5 shows about the relative strength of these alloys when the percentage by mass of magnesium changes. You can see that as the percentage by mass of magnesium increases, the strength increases, and look, it's a straight line, it's a linear relationship. Determine using figure 5 the percentage by mass of aluminium in an aluminium-magnesium alloy with a relative strength of 103. Let's read along here. Come down that x-axis. You can see it's 3% magnesium. So again, we're being asked about aluminium. So the answer here is that it's 97% aluminium. Metal objects can be electroplated with gold. Give 2 reasons why metal objects are electroplated with gold. Lots of answers here. You could say to improve the appearance because it's cheaper than using solid gold, to increase the resistance to corrosion because remember gold is very unreactive. This question is about electrolysis. A sample of molten potassium bromide is electrolyzed. What are the 2 products formed? So we have K plus, Br minus. So I'm just going to quickly show you with these half equations. Hopefully you can see, therefore, we're going to make potassium and bromine. Option D. Zinc chloride and zinc carbonate contain ions. Zinc chloride mixed with water can be electrolyzed. Zinc carbonate mixed with water cannot be electrolyzed. Explain this difference. It's all to do with their solubility. Zinc chloride is soluble, whereas zinc carbonate is not. Feel free to write these out in words, by the way. The ions are free to move in the zinc chloride, which enables them to undergo electrolysis. In the electrolysis of sodium chloride solution, bubbles of a colourless gas form at the cathode. This is the negative electrode. This gas, when mixed with air, burns with a squeaky pop. Identify this gas. Okay, if you don't know anything about electrolysis, hopefully you're aware that it is hydrogen that burns with a squeaky pop. But let's just have a look at what's going on at the cathode. Remember I said that was the negative electrode. You've got your hydrogen ions turning into H2 gas. Make sure that's balanced. You do actually get a mark if you provide this half equation. So we're just going to say the hydrogen ions are attracted to the cathode because they're oppositely charged and are reduced. Why? Because they gain electrons. A solution of copper sulfate in a beaker is electrolyzed using copper electrodes. Draw a label diagram to show how this experiment would be set up. The beaker has been drawn for you. So here's our copper sulfate solution. There's our anode, there's our cathode. During the electrolysis, the anode gets smaller, the cathode gets larger, and the solution remains the same shade of blue. Give the reason for each of these observations. So why does the anode get smaller? That's because the copper atoms form ions and go into solution. Why does the cathode get larger? Because copper atoms are formed from the ions in the solution. And lastly, why does the solution remain the same shade of blue? Because the same number of ions enter and leave the solution. Copper carbonate reacts with dilute nitric acid. During the reaction, the copper carbonate powder completely disappears. State what can be deduced about the amount of acid used. The acid must be in excess. During the reaction, the pH of the mixture changes from 2 to 6. By what factor has the concentration of hydrogen ions in the mixture changed? So let's have a look. We've gone from pH 2, 3, 4, 5, and 6. And remember, the pH changes by a factor of 10 each time. It's becoming less acidic as that pH increases. So just count it. 1, 2, 3, 4. 1 times 10 to the 4. So it's this one here because it's getting less acidic. Using different reactants, a solution of copper sulfate was prepared. Describe what should be done to obtain copper sulfate crystals from this copper sulfate solution. You want to heat the solution to evaporate some of the water and then leave to cool and dry. On filter paper if you're feeling fancy. When chloride ions are added to a pale blue solution containing copper ions, the mixture turns yellow. This is a reversible reaction. What effect does the removal of chloride ions have on the colour of the yellow mixture? So if we remove chloride ions, the position of equilibrium shifts to the left to replace them, so we will see it turn blue. Hydrated copper sulfate has the formula. The formula tells us that each mole of copper sulfate contains 5 moles of water. A sample of this was heated until all the water was removed to form anhydrous copper sulfate. The mass of water formed was 4.5 grams. Calculate the mass of hydrated copper sulfate that was heated. Okay, you can see that I've copied that equation down. I'm going to show you how to set this answer up nice and simply. We're going to write mass, mR, number of moles. We're using this formula triangle, which states that mass is mR times number of moles. Put in the information we've been given. We know we have 4.5 grams of water. We're being asked for the mass of hydrated copper sulfate, so we're putting the X there. The mR we've been kindly given is 249.5. What about the mR of water? It's 18 because we're doing 2 times 1 plus 16, so that becomes 18. Then do 4.5 divided by 18 in order to find the number of moles. We're doing that because it's mass divided by mR to get 0.25 moles of water. Check your mole connection, it's 5 to 1, so we divide that number by 5 to find the number of moles of hydrated copper sulfate. And then lastly, to find X, we do mR times number of moles, so multiply these two numbers together to get X equals 12.475. The order of reactivity of copper, magnesium and zinc can be determined by the displacement reactions between these metals and solutions of their salts. You are provided with samples of the 3 metals, solutions of their salts. Describe the experiments that can be done to determine the order of reactivity of these metals by displacement reactions. So firstly, you want to place separate pieces of each metal into solutions of each salt. Then you want to observe changes in appearance of both the metal and solution. And you'll find that the more reactive the metal, the greater the number of reactions that will take place. Metals can be extracted from ores found in the Earth's crust. Explain why aluminium cannot be extracted from its ore by heating with carbon, but can be extracted by electrolysis. So aluminium is more reactive than carbon. That's why it can't be extracted by heating with carbon. However, electrolysis enables the aluminium ions to be reduced, because if you think about what happens in that electrolysis chamber, you get your Al3+ ions, you're reducing it by adding 3 electrons in order to form that Al metal, which is after all what you're after. Titanium is extracted from its ore in several stages. In the first stage, titanium chloride is formed as a gas. The gas is cooled to form liquid titanium chloride containing dissolved impurities. Suggests how pure titanium chloride could be separated from the impurities. Okay, we've got liquid. We want to use simple distillation or fractional distillation in order to separate this out. In another stage, the pure titanium chloride is reacted with 500 moles of magnesium and excess. Calculate the number of moles in 45,000 grams of titanium chloride. So number of moles is the mass, which is 45,000, divided by the MR of titanium chloride. We want to do 48 plus 4 lots of chlorine to get 236.8. Show that the 500 moles of magnesium added is in excess. So the way we do that is by working out the mole connection. So if we know we have 236.8 moles of titanium chloride, how much magnesium would we need to react with that fully? Use this 2. You need to double that number. To get 473.6 moles, but they're given us 500, which means that the magnesium is in excess. So let's really spell that out. So we've really spelled that out, saying that we need 473.6 moles, but we've been given 500. After this reaction, there's a mixture of solids, magnesium, titanium, magnesium chloride. Titanium does not react with dilute hydrochloric acid. Suggest a simple method to separate titanium from the mixture. What you want to do is filter the mixture in order to remove the titanium and then wash the titanium. Hydrogen-oxygen fuel cells, rather than chemical cells, can be used to power some vehicles. Give one advantage of using hydrogen-oxygen fuel cell rather than using a chemical cell to power a vehicle. The main thing here is that chemical cells contain toxic substances which need careful disposal of afterwards, or you can say that a hydrogen-oxygen fuel cell provides a constant voltage. Complete the half equation for the reaction taking place at one of the electrodes in a hydrogen-oxygen fuel cell. I think the easiest thing here is to just learn this off by heart, unfortunately. Calculate the volume of 48 grams of oxygen at room temperature and pressure. First of all, we need to find the number of moles by doing the mass divided by MR. So it's O2, so we do 16 times 2. Once you put that into your calculator, you'll get 1.5 moles. And then to find the volume, you do 1.5 moles multiplied by 24, because they've told us that 1 mole of any gas occupies 24 decimeters cubed, to get an answer of 36. The hydrogen used in the hydrogen-oxygen fuel cell can be produced from methanol. In this reaction, the forward reaction is endothermic, and heat energy is taken in from the surroundings. The conditions used for this reaction are a nickel catalyst and a temperature of 220 degrees Celsius. Explain in terms of their effects on the rate of attainment of equilibrium and the equilibrium yield of hydrogen, why the reaction is carried out using a catalyst at 220 degrees rather than without a catalyst at a low temperature. It's quite a wordy question, that, but let's start by saying why we want a high temperature. A high temperature is needed. This is all about understanding Le Chatelier's principle and equilibria. So remember, high temperatures will favour the endothermic reaction. In this case, we know that the forward reaction is endothermic. The position of equilibrium shifts to the right in order to produce a large yield of hydrogen, which is a good thing. So we'll start by saying that. So a high temperature is needed because the forward reaction is endothermic. And the position of equilibrium shifts to the right, increasing the yield of hydrogen. From a rates of reaction point of view, high temperatures are good. Remember why? Because the particles have greater kinetic energy and there's an increased frequency of successful collisions. And then if we talk about the catalyst works by increasing the rate of reaction. Because it's a reversible reaction, it will increase the rate of the forward and reverse reactions equally. But that's not a bad thing. It still increases that all-important reaction that produces hydrogen. How does the catalyst work? By offering an alternative reaction pathway with lower activation energy. An ion of element X can be represented as this ion of element X has 54 electrons. Calculate the number of protons and the number of neutrons in this ion. So the main thing here is to notice that 2 minus charge. It means it has therefore 2 more electrons than protons. So we can therefore infer that it has 52 protons. And then to find the number of neutrons, we do the mass number 125 minus that proton number that we've just calculated to get 73. A sample of silicon contains isotopes. State in terms of subatomic particles how atoms of these isotopes are the same, because they have the same number of protons but a different number of neutrons. This sample of silicon contains 3 isotopes. Calculate the relative atomic mass of silicon in this sample. So to do this, we simply multiply the percentage by the mass number, add it to the percentage multiplied by the mass number, add it to the percentage multiplied by the mass number, divide by 100. So I'll show you that now. Make sure your answer is sensible. The mass should sit somewhere here, which it does. Figure 6 shows some properties of 3 substances A, B and C. Deduce using the information in Figure 6 the structure and bonding of substances A, B and C, explaining their properties in terms of their structure and bonding. So A has a high melting point, so it's a giant structure. The fact that it doesn't conduct when solid but does when it's molten means it's giant ionic. You must learn these characteristics. Substance B again has a high melting point. It's got good conductivity when solid and molten, which means it's most likely giant metallic. Substance C has a very low melting point. It's got poor conductivity. These properties are indicative of a simple molecular or simple covalent structure. So let's start with substance A. Substance A is a giant ionic structure. So we're going to say why it has a high melting point with strong electrostatic forces of attraction between oppositely charged ions, which require a lot of energy to break. Then we need to point out why it conducts when molten. because the ions are free to move. Substance B now, remember we said that was a giant metallic structure. So it has a high melting point because it has strong electrostatic forces of attraction between positive metal ions and this sea of delocalized electrons. We always talk about the requirement of energy. It requires a lot of energy to overcome these forces. Why does it conduct when molten and solid? Because it has delocalized electrons which are free to move. And then finally, substance C is a simple covalent structure with weak intermolecular forces which do not require a lot of energy to break. And then why doesn't it conduct? Because it has no free ions or electrons. This is a very full answer. My hand's hurting. A sample of solid potassium hydroxide contains soluble unreactive impurities. A student tried to find the mass of potassium hydroxide in the sample using the following method. Step 1, measure the mass of the sample of impure potassium hydroxide. Step 2, dissolve the sample in 250 centimetres cubed of water in a beaker. Take a 25 centimetres cubed sample of the potassium hydroxide solution using a measuring cylinder and pour into a conical flask. Add 3 drops of indicator to the solution. Put the conical flask on a white tile. Using a burette, add dilute sulfuric acid of known concentration drop by drop to the solution while swelling the flask. Continue adding the sulfuric acid until the colour of the solution changes. Record the volume of sulfuric acid added. Use this result to calculate the mass of pure potassium hydroxide in the sample. Suggest 3 ways to improve this method to obtain a more accurate mass of pure potassium hydroxide. Yeah, we don't like using the measuring cylinder. Why not use a pipette? Down here, we want to be adding the sulfuric acid dropwise towards the end. And let's just point out that they should have carried out a rough titration beforehand to get a good idea of what volume they'd need. The indicator used was phenolphthalein, which row shows the colour change that would be seen in this titration. So because you're starting with an alkaline solution, you're going to start with it being pink and then the end point will be colourless. So the answer here is C. Another student carried out the titration accurately. 12.15 centimetres cubed of dilute sulfuric acid with a concentration of 0.10 moles reacted completely with 25 centimetres cubed of potassium hydroxide solution. Calculate the concentration of this potassium hydroxide solution. So you can see I've copied down that equation again. You should rewrite it yourselves in the exam. This is a very important formula triangle here. So we're going to lay it out using our table again. This time we're having number of moles, concentration and volume. just make sure you put all of these numbers in the correct place. So our volume of sulfuric acid is 12.15. Just be careful, it needs to be in decimeters cubed, so we need to divide that number by 1,000. We know that its concentration is 0.14 moles. Our volume of potassium hydroxide was 25 centimeters cubed. Again, we need to convert that to decimeters cubed. We're being asked to find the concentration of potassium hydroxide solution. Hopefully you can see that we have enough information here to find the number of moles of sulfuric acid. We do this by doing concentration times volume. So do 0.14 multiplied by brackets 12.15 divided by 1,000 to get 0.001701 moles. Check your mole connection, it's 1 to 2, so we multiply that number by 2 to find the moles of potassium hydroxide. And then last step is to find the concentration by doing number of moles divided by volume. So X equals 0.136. The different solution of potassium hydroxide has a concentration of 0.15 moles. This potassium hydroxide solution was made by dissolving 2.56 grams of potassium hydroxide to form 25 centimeters cubed of solution. Calculate the percentage by mass of potassium hydroxide in the impure potassium hydroxide, and there's the MR. So this is quite hard actually. You want to find the number of moles first of all by doing mass divided by MR. So we know we have 2.56 grams divided by the MR, we've been told is 56. So there's our number of moles. But be careful, that's in 250 centimeters cubed of solution, and this concentration value is per decimeters cubed. So there are 1,000 centimeters cubed per decimeters cubed. So effectively we have 0.25 decimeters cubed, which is why I'm going to do that in order to sort out my units to get 0.1828 as our concentration. And now because our concentration units align, we can now do 0.175 divided by that number in order to find the percentage by mass of potassium hydroxide. So it's 95.7%.